Hello and welcome back to this course for psychologists and social scientists on causality. We're now in session 7 for machine learning for plugin estimation, parameter estimation. So plugin estimation, or sometimes called substitution estimation, is the same as this parameter estimation goal when we have a parameter that's probably a causal parameter, for instance, and we want to estimate it. And we want to do so using machine learning models. So in contrast with linear models, which spit us out some nice sets of coefficients, which are readily usable, assuming we've correctly specified the model and so on. We also get all the statistical inference and so on. In contrast, machine learning models, they're predictive models and they don't necessarily have corresponding coefficients. You could argue that a linear regression is also a machine learning model. I probably would argue that, but for the most part, these machine learning algorithms are highly parameterized. They don't give you these summary coefficients out, and so we're going to have to derive them. And the way we derive them is actually, as we've seen before, we show some examples using linear models. We can do the same with any predictive model if we have some way to use that model to generate predictions. And so let's say we specify our theoretical estimand as follows. The average treatment effect is the difference between the expectations of the outcome y under treatment equals 1 and under treatment equals 0, assuming when I say under, I mean I've done treatment with this do operator and done not treatment or the control group using also the do operator. So this is a theoretical estimand. It kind of simulates or represents the fact that in an ideal case, we'd be able, in an ideal world, we'd be able to experiment on the quantity of interest to generate data that are not complicated by unobserved confounders or confounders and so on. And as we said before, the goal of identification is to move from this theoretical estimand that's expressed in terms of do calculus into something that is estimable from the data. And so this sort of unidentified quantity in this case might look something as follows. At least for the backdoor criterion, we are able to identify a set of variables x, which we can condition on in order to block backdoor paths. And sometimes that's not possible, but assuming that it is, we might be able to rewrite the ATE rather than using do calculus, write it in terms of estimable quantities here. So we have the difference in these expectations, and rather than just having do t equals 1 and do t equals 0, we now just condition on t equals 1, condition on t equals 0, and we include also the condition of a set of variables, which is why this is in bold font, a set of variables x, which block those backdoor paths. Notice also we've got an outer expectation here, because if we're conditioning on something else, we're essentially subsetting the data again, and we don't want to have lots of different estimands. If we're interested in the average treatment effect, we just want one estimand, so we have to then take averages over those subgroups. So we have this extra outer expectation over x here. And we can use DAGs, as we've seen, for choosing X. Okay, so that's all well and good. We've covered that before. So what is plugin estimation in this case? Well, again, just repeating what we had on the previous slide, if this is the estimand expressed in terms of estimable quantities, we want to be able to estimate these expectations. And so what we can do is rewrite this in terms of an empirical quantity. So now I've put sort of a hat over this ATE to say that it's an estimate for that quantity. And instead of these expectation terms here, I'm going to have Q. And Q is going to be our plug-in estimator. It's going to be a machine learning algorithm. It can be a linear model like we've seen earlier in the course, where we created these two data sets and we fed them through our models and then we generated predictions. Well, that's exactly what's represented here. We're going to take Q. It's a machine learning algorithm that's been trained, or it's a linear model that's been fit. And we're going to pass into it the data set for when t is set to 1 and then when t is set to 0. We're going to generate those estimates for the expectations of y given x. So this is going to be on a sort of per row basis in our data set. And we're going to get the difference between those two. And so this is a long list for each row of data that we feed into this algorithm. We're going to get estimates for the outcome under those two interventional situations. And then we just sum up all those results and average them, and that's what gives us our average treatment effect. So this is called a plug-in estimator, because essentially, even though this is the parameter of interest, we're sort of plugging in an estimator to fulfill the role of the estimation of these expectations. So Q, as I said before, it's super simple. This is just, for instance, your random forest. In both cases, the same random forest, and we're going to feed it different data to generate predictions. So as I say, Q is a function taking in treatment and X as arguments. They're the predictors, and it's going to generate an approximation for our expected value of the outcome given those predictors. As I said before, we have seen this already. In fact, this is the code. Sorry, the arrows have not manifest very well here. So when we train a linear model, we're essentially doing the same thing. We're fitting a model Q, which is designed to approximate the expected value of y given t and x. Here, y is this variable c, a is maybe just, maybe we don't need any conditioning set, x is our treatment variable. But then we create these interventional data sets here where t is equal to 1 in this first case, t is equal to 0 in the second case. We've got different variable names in the original example. And then we generate predictions under those two data sets using the model we already trained. And then we just take the difference and take the mean of those differences. And so that's what gives us this expression here. So C do 1, in other words, the predictions under treatment equals 1 is this first Q, t equals 1 and x, and then C do equals 0 is essentially when we've intervened on the data set, setting t equal to 0, and we generate those predictions. And then here we're taking the difference and averaging them. So the only difference that we're going to think about now is rather than using linear models, we're going to use machine learning algorithms. And indeed, just like I said at the beginning of the machine learning basics section, really, this is just a case of swapping out the linear model for a machine learning model, but also making sure that we're doing everything that we can to not overfit the data, to make sure we're doing reasonable train test splitting and so on, as part of any sort of good practice for training machine learning algorithms. So for the example, I'm going to use this graph, which is what we saw in the previous session. Again, I'm going to generate some data according to this graph. Still linear for now. It doesn't really matter that we're dealing with linear systems in terms of the data generating process. We just want to make sure that the machine learning is going to do what we want it to do. And so if we look at this graph, we can identify the causal effect, which I'm assuming is the effect of x on y, the total effect. So it's going to go through m as well. And as part of the process of designing our regression model, we have to identify the variables that block the backdoor paths. So there's a variable C1 here, and there's a backdoor path that's non-causal that goes from x to C1 to m to y. So we have to block that by including or conditioning on C1. We also have another backdoor path here that's non-causal from x to C2 to C5 to y. So we can include C5. You could also include C2, or you could include C2 in place of C5, kind of up to you. And then we have C4 here, which is a collider, so there's no backdoor path here. We have a couple of risk variables here, which might help explain some of the variance in Y that helps us narrow the standard errors in the effect of X on Y. For now, it's not a big deal because we're actually not going to look at statistical inference with machine learning yet. That's going to be in a later section. But something to bear in mind that you can include these risk variables here. Don't include D, don't include I. Again, look back to the DAG cheat sheet that I created with which variables are good and bad controls to make sure that you're happy with which variables to include. And we can actually compute the true effect here. The total effect of X on Y is the multiplication of 0.6 with 0.8. Add in, and then we add 0.4. So that's here 0.4 plus 0.6 times 0.8 is 0.88. So really we want to check that we can recover this true effect using machine learning in this plug-in estimation sense. Note, we could have also introduced some nonlinearities into the data generating process. You could have also used some binary data using the R-binom function as well. We're going to see a little bit of an example later on just to make sure we're happy with simulating data when there's nonlinear processes, to make sure that we can still compute the total effect, because then it gets a little bit more difficult to do analytically. So we might want to just simulate the data with a huge sample size first, calculate the total effect by generating the potential outcomes for Y under treatment, for Y under no treatment, so that we have a reasonable estimate of the true effect. But we'll see that later. So I'm going to start just by generating all those data according to that process. Here I've got a big data set here. You can try smaller data sets if you wish, or even bigger. And as I said, the true effect is 0.88. So that's what we're trying to make to estimate. So I'm going to start by doing a train test split using exactly the same process we had before, 60% for training, 40% for testing. In my random forest, I'm going to specify the outcome Y, and then I'm going to specify a finite set of, they're always going to be finite, but a limited set of predictors based on the backdoor criterion. So R1 and R2 were the precision variables, the risk variables that aren't needed to block backdoor paths. We have X here, which is the target, the treatment variable, and then we have C1 and C5, which are doing the job of blocking those backdoor paths. So this is our random forest. We're going to generate some predictions on the test set here, and we're just going to look at the test performance and the baseline performance. In fact, I've noticed there's a mistake here. This shouldn't be Pred's test. This should be all test split $y in here, so something to watch out for. I've also generated the variable, I've also generated the variable importances here, just to check to see what happens, and it tells us that X is the most important variable. That's reassuring, and then followed by R2, C5, C1, and R1, just as a by the way, just to check the variable importances. So again, here, when we're fitting this model, we're essentially fitting our Q function, which is designed to model the expected value of Y given X and some variables or covariates W. At that point, I'm going to do this interventional step. So I'm going to create some data, and maybe this is a bit of an easier way of doing it. So I'm going to create copies of the data set. So first, data do 1, I'm just going to set equal to data. And then I'm also going to have data do 0 is also equal to data. So I've just got 3 copies of data now in my environment in R. And then I'm going to set the variable X in data do 1 to 1 and set the variable of X in data do 0 to 0. So we're intervening on that data set. And it's important to note that whilst we need train, test, and validation and cross-validation for model selection purposes, actually, when it comes to parameter estimation, so long as we've used some process like train, test, validation, cross-validation to select a model in a reasonable way, so we're not using the test set to select a model that does really well for prediction, once we've got that model, we can then actually retrain that model on the entire data set and generate estimations for the entire data set. So it's a little bit different to the general supervised learning case, where we really want to keep a separation between the training and the testing data. For causal inference, once we've done that train, test, splitting, and validation to derive a model that we're happy with, then we can retrain that model on the entire data set and generate predictions under these 2 interventional situations. So you can see here, for instance, when I pass in my new data to this random forest, I'm passing in the full data set. The only step that's missing here that you can do is to retrain this forest also on the entire data set. And then we compute the differences between these predictions, and we get an estimate for the difference between these two to be 0.88, which is actually very close to the true model. And indeed, if I run a linear model on this, just to fulfill the same process that we did in the previous examples earlier on in the course, we can see that actually we don't do quite as well as the random forest in this case, which is bizarre because actually the linear model is the correct model. So this must just be due to sort of finite sample variation. But nonetheless, we get close to the result, just to check that we get sort of similar results in both cases. And so as before, this process of intervening on the data set, feeding those data sets to the random forest, generating new predictions is essentially computing the values in this expression here, where we have Q under this X equals 1 and then Q under X equals 0. And then we generate our estimate for the average treatment effect. So interestingly here, as I said, the random forest did better than the linear model, although in this example, the linear model was the correct model, so it should have done better, arguably, because we knew that the data were actually generated via a linear process to begin with. So the next example I want to do is actually just to show the same process using a super learner. There are 2 packages that I'm aware of actually for super learners, and this first one, I mean, I'm going to use both in case you have a preference, but later on, I'm going to use a slightly different package. So this one, I'll use the super learner package, and the later example, I'll use the SL3 package, I believe. But it doesn't really matter, just to give you exposure to both. The process and the thought process is the same. Here, instead of passing the data directly to the model, we can actually separate the data into the set of predictors and the outcome. So here the predictors are the set of data that we had, X1, C1, C5, R1, and R2, and then the outcome is Y. List wrappers tells us all the possible models that we can use in the super learner. It will give you a big long list, and then from there you can select, for instance, SL.mean, which is just predicting the mean outcome, SL.lm, which is the linear model, SL.random forest, which is a random forest, and SL.polymars, which is a polynomial spline model, I believe. So we can specify that library of learners in our super learner, specify the outcome, the predictors. Family here allows us to say whether the outcome is, say, binary or categorical or continuous. So here it's continuous, so we're just going to say the family is Gaussian. And then we have to specify the inner and outer loops, because this is going to do some cross-validation for us. Once we fit that, and it can take a little while to run, we can run the summary. Let me just catch up here. Oh yeah, you can also use many more candidate learners than this if you want. You can include many more algorithms, and you can also include algorithms with different hyperparameters and so on. This is just a small selection to make sure that we can run it and to not take too much time. And you may also, by the way, have to install the packages that are relevant to these algorithms as well. They may not be included when you install the superlearner package. So here is going to give us a summary of the performance under the different folds and also the coefficients, because if you recall, the process for fitting a superlearner is as follows. For each candidate learner, we go through this cross-validation process. We generate predictions on the validation set, and then we use that validation set to fit a meta-learner, which essentially fits a set of coefficients to each of these learners as if it's sort of like another level of prediction. So rather than the original variables in the data set, now we have a data set that comprises of predictions from each of the predictions of the outcome from each of these independent learners. And then we fit a linear model on that to predict the outcome. And we get a set of coefficients that reweight the balance and the combination of the predictions from each of those candidate learners. So once we've got these coefficients, we can then refit each of the candidate learners on the entire data set and weight their predictions according to the coefficients that we learned in this step here. And so when I go through here, we can actually get those, the average weighting for each candidate learner over all the validation folds. We can pull those out using this function here. And it's also worth noting that when we fit this superlearner, we're going to end up with coefficients that are all non-negative and all sum to 1. So it's not just a simple linear regression here. It's sort of like a constrained linear regression. We have some constraints on the values of those beta coefficients in that meta-learner. So this is the output. We get the algorithm name here. We have the superlearner, which is the overall superlearner's performance. We also have discrete superlearner, which just gives us the best performing single learner from the group of candidate learners. And then we have all the individual performers here. So the mean, the linear model, the random forest, and the polynomial spline. What we find is actually that the superlearner, there's only one model actually we're using well, which is the linear model, which is reassuring because this is a linear data set. So that gives us the best performance here of 1.7 in terms of the error. And actually the discrete superlearner is the same because we're not using the other models, or at least very little. So we can compare to see what the superlearner used under each of the individual folds in our cross-validation. And we can see that the superlearner didn't use the random forest, which might be surprising, or the mean prediction, which is not so surprising because it's not a very good predictor, almost entirely preferring the linear model with a little bit of the polynomial spline. So if you look at the weightings for each of these models, here we have the mean prediction, the linear model, the random forest, and the polynomial spline. These are the coefficients on each of those. So these sum up to 1. And we also note that the mean was never used. There's 0 on the mean model for every single one of these folds. There's 0 on the random forest for each one of those folds. And then for the most part, we use just the linear model with a little sort of dash of polynomial spline. So that helps us understand also what the underlying functions are in the data, because if it's clearly preferring the linear model, we might make strong inference that actually it's at least close to a linear process. Now we know it's a linear process, but in practice you may not. And so once we've got that, we can actually retrain those models on the full data and then reweight them according to the average coefficients across all these k-fold splits. So here I pull out the linear model. I specify the outcome, the predictors. I train it on the full set of models, full set of data. Sorry. Same with the polynomial spline. They're both trained on the full data at this stage. We can create these interventional sets of predictors. When I set x equal to 1 and I set x equal to 0, I can generate predictions using these individual models, and then I can reweight their contributions and create a weighted combination of them both using the average coefficients from this table here. And indeed, I compute the average here. So the average coefficients I can compute in this step. Okay. So here we go. This is reweighting them, combining them to get the combined predictions of the superlearner, and I can compute the difference here where we get 0.89, which is an overestimate in this case. So just obviously this is using real data, real data, it's using a finite sample. There's going to be some variation there. Here are all the steps. So we've been using linear data generating processes so far, and this made it very easy to calculate the true effect size because we could just look at the original graph and look at the path coefficients, and for each path we can multiply the coefficients and then sum the paths together. But obviously this is more difficult if the data generating process is nonlinear, because we don't just have a single path coefficient for each of these arrows, but we have some function there. So it's really, when you move over to machine learning and you start simulating data, you may well want to simulate nonlinear processes. So I just want to show you how to do that in a way that's quick and easy. So you don't have to start computing, the effects in sort of analytical way, but you can still do it relatively painlessly. So just as an example, I'm going to actually abstract the data generating process as well, which is good practice. So I'm going to create a function now called DGP, data generating process. And this function is going to take in n, which is the sample size. All of this looks the same. I generate the random noise. These could be binomial, but here they're random normal. I'm going to keep everything simple, but I'm just going to introduce a little bit of nonlinearity here. So the outcome here is now including x, but also x squared and also x cubed. So rather than now having to compute the path coefficients when you have this sort of polynomial structure, it could be arbitrary. I'm going to show you what happens under the interventional situation. So here, when x equals 1, I just compute the outcome. So I have y1, which is essentially the counterfactual outcome under treatment. So I set x equals to 1, and I generate that as a new variable, y1. So x here is just set equal to 1. So x is just 1, x squared is 1, and x cubed is 1. So I end up with this expression for y1. And then for y0, when x equals 0, all of these terms become 0, and I end up just with 0.3 times c plus uy. And I can compute the average treatment effect now by just computing the difference between y1 and y0. That's the difference between those two counterfactual outcomes. So again, in reality, we definitely don't have access to this. If we did, we wouldn't need to do any causal inference. And then I can return both the data, which doesn't include the counterfactual outcomes or the average treatment effect, and I can include the average treatment effect. Or you can return whatever you want, obviously, in practice. So now when I say run this function and I pass in, say, 1 million data points, I can pull out the estimate for the ATE, which will be very, very close to the true value of the ATE because of the sample size is so high. So because this is a list, I can pull out the second item in the list, and it will give me the ATE that I generated here. And so when you do this process, you can run it first using, say, 1 million data points to get the ATE, and then you can just reduce the number of data points. You can either select from a subset of this, or you can rerun it just with, say, 600 in here, and then you can regenerate that. In which case, you'll have an empirical estimate of the true ATE as well. You'll have the empirical kind of value for the average treatment effect, still the true value, but not the true value in the limit of infinite data. So that's it for this part of the course, and I look forward to seeing you in the next one.